Good morning students. Today we are going to discuss the topic of normal modes of vibration of triatomic molecules. Basically, in triatomic molecule, the vibration are of two types. First is stretching vibration. Second is bending vibration. What is meant by stretching vibration? In this type of vibration, this type of vibration arises due to the stretching and contracting of bonds without producing any change in the bond angles. That is, the distance between two atoms increases or decreases, but the atom remains on the same bond axis. Your stretching vibration are further classified into two types. First is symmetric stretching. Now, what is the meaning of symmetric stretching and asymmetric stretching? We are first going to discuss it. This is the rubber band. If I pull both the end of this rubber band, so this type of stretching is what? Symmetric stretching. So just see here, in this type of stretching, moment of bonded atoms is in the same direction with respect to central metal atom. That is, both the bonded atoms move towards or away from your central metal atom. So just see here, in this diagram, this is the ozone molecule, and both the oxygen simultaneously go away from your centered oxygen atom. Or just see in this diagram, both oxygen come closer or they contract towards your central metal atom simultaneously. So this type of stretching, it is symmetric stretching. So this is symmetric stretching, or both sides come inside, so it is also symmetric stretching. Now, what is meant by asymmetric stretching? So again we are taking the help of this rubber band. Just see that I fix the position of this end and I just stretch this side. So this is only stretch on one side. So this type of stretching is known as asymmetric stretching. So in this type of stretching, one atom approaches towards center atom, whereas other atoms moves away from it. So again see, in this example of ozone, this oxygen which are present on left hand side come closer towards your centered oxygen, while this oxygen which is on right hand side go away from your centered oxygen atom. So this types of stretching is known as asymmetric stretching. Now we are going to see bending vibration. In this case of bending vibration, there is deformation of bond angles and there is no change in bond length. It is important. Bending is related with your bond angle. There are four types of bending vibration. So first we are going to see scissoring. Now what is the meaning of scissoring? So just see, if this is your ozone molecule, this is the centered oxygen, this is second oxygen, this is third oxygen. Now we know that now when I go for scissoring motion, just see what happened with the bond angle. Now scissoring motion is like this. Both atoms simultaneously come together or they simultaneously go away. So it in a scissoring bending, your bond angle either increases or decreases. So it is a scissoring bending. Now Second type is rocking bending. Now just see what happen when I go for rocking motion with this molecule. So in this motion, just see both atom, that is both oxygen atom, goes either towards left hand side or right hand side. They move simultaneously in one direction. So this type of motion is rocking. Okay. Now just see what is wagging. So just see in this type what happened with the plane of a molecule. This is the plane of molecule. Now what happened with the plane of molecule. So in a wagging, both oxygen atom, that is which are present here and here. So wagging motion is like this. Either it go this side or this side. It go either this side or this side. This is a wagging motion. So it is out of plane bending. Now next is twisting. There is a chance that one atom goes on this side, second come this side, and motion like this. So it is known as twisted bending. So in this type of scissoring, in this type of vibration, the two atom approaches in same plane. In rocking, in this type of vibration, movement of atom occurs in same direction and also in same plane. In wagging, in this type of vibration, the two atoms move up like this and down the plane with respect to central metal atom. Twisting, in this type of vibration, one of the atom moves up, other moves, one of the atom moves up the plane and other moves down the plane with respect to central metal atom or central atom. Now it is important, the energy needed to stretch a bond is more than that needed to bend it. So the stretching absorption always appear at higher frequency. It is important. Stretching vibration are always appear at higher frequency and bending than your bending absorption of the same bond. Now question of 4 mark generally asked on normal modes of vibration of CO2 or water. So we are going to discuss normal modes of vibration in CO2. So CO2 is linear molecule, hence the normal modes of vibration are given by this formula, that is thrice n minus 5, where n is number of atoms. So 3 multiplied by 3 minus 5 is equal to 9 minus 5, which is equal to 4. So there are 4 normal moles of vibrations. So these 4 mode of vibration are classified as symmetric stretching vibration, that is nu bar 1. Second is asymmetric stretching vibration, that is nu bar 2. Third is inner plane bending, that is nu bar 3. Fourth is out of plane bending, that is nu bar 4. Now out of these 4 vibrations, which are IR active and which are IR inactive? your symmetric stretching vibration are IR inactive. Your asymmetric stretching vibration are IR active. Your plane bending are IR active. Out of plane bending is also IR active. These two bending vibration are degenerated. Now, why your symmetric stretching vibration are IR inactive and other is active, we are going to see it. Out of 4, symmetric stretching vibration does not produce any change in dipole moment, and hence such a vibration is IR inactive. It is important. Due to symmetric stretching, there is no change in dipole moment of your CO2. That's why symmetric stretching vibration are IR inactive vibrations. Asymmetric stretching vibration are accompanied by change in dipole moments, hence they are IR active. Two bending vibration are also IR active, and the energy required in both of them is equal, and therefore they are degenerated. That is, nu bar 3 is equal to nu bar 4. So generally symmetric stretching vibration frequency for this, it is 1340 centimeter inverse. For asymmetric stretching, it is 2350 centimeter inverse. And for bending vibration which are degenerated, frequency is 667 centimeter inverse. Symmetric vibration are IR inactive, or symmetric stretching is IR inactive. Asymmetric stretching is IR active, and bending vibrations are IR active. Now we are going to see normal modes of vibration in water. Water is not a linear molecule. That's why normal mode of vibration is thrice n minus 6. So n is number of atoms in a formula. So 3 multiplied by 3 minus 6, that is 3. So say there are 3 normal mode of vibration, which are divided as symmetric stretching vibration, that is nu bar 1, asymmetric stretching vibration, that is nu bar 3, and symmetric bending vibration, that is nu bar 2. Now it is important, out of these 3, which are IR active and which are IR inactive. Symmetric stretching vibration is IR active. Your symmetric bending is also IR active, and asymmetric stretching is also IR active. Don't get confused that always symmetric stretching are IR inactive. It is not like so, because the condition is, if there is change in a dipole moment due to symmetric stretching, then that symmetric stretching is IR active. If your symmetric stretching or any other stretching or bending vibration does not produce any change in a dipole moment, then they are simply IR inactive. So in a case of CO2, we see that this symmetric stretching does not produce any change in a dipole moment. That's why it is IR inactive. Now we are going to see how symmetric stretching vibration produces change in the dipole moment. So just see, in the symmetric stretching, your both hydrogen goes away from oxygen while oxygen goes upward. This type of stretching generally causes change in the dipole moment. So in a case of water, dipole moment changes due to symmetric stretching. That's why this is IR active stretch. So it comes as 3652 centimeter inverse. Symmetric bending, in this case both hydrogen goes away like this, oxygen comes inside. So it is also IR active. Its frequency is 1596 centimeter inverse. While asymmetric stretching also produces change in dipole moment, that's why it is also IR active, and it comes nearly 3759 centimeter inverse. Now always try to compare the value of asymmetric stretching and symmetric stretching. So we see that in both the example, asymmetric stretching comes at higher side as compared to your symmetric stretching, and your bending vibration values are always less than stretching vibrations. In our next class, we are going to start with the topic of electrochemistry. Thank you very much.